Welcome back to LabRat Scientific. Now today I want to talk about the concept of a moment. So what precisely do I mean by a moment? Well, we can take a look at this little device here. I have a beam and I have a nail which represents a pivot point. So obviously the beam wants to move around that pivot point. Now a moment is when I apply a force at some point along the beam, and so it's the force times that moment arm which makes the beam want to rotate or move. Now we can look at this from two perspectives, from a dynamic perspective or a static perspective. If we're looking at it from a dynamic perspective, we want to look and see how this beam is going to move. However, if we want to look at it from a static perspective, we need to consider that all the moments involved are equal and opposite, and so the total sum of those moments are zero. So let's take a look at a diagram that shows the setup we'll be using for this experiment. Here's a simple diagram of the test setup we'll be using. First of all, I have a support with a pivot point, and to that support I'll attach a beam. I'll be using a scale to measure forces, and I attach that scale to the beam using a string. Then I'm going to hang one or more test weights from the beam at various locations to see how the supporting force changes depending on the weights and positions of those test weights. Now, the test weight is going to create a clockwise moment around the pivot point. And in turn, the scale will be pulling upwards to counteract that moment, and it will create a counterclockwise moment. Now, since it's a static problem where the beam isn't moving, the moment in the counterclockwise direction needs to equal the moment in the clockwise direction. So here's my physical setup. I have a mast here, which has a nail which serves as the pivot point. You can see my beam also has a hole in it and can rotate freely on my axle. I've also got a force measuring device, in this case an electronic scale. Now we could use a mechanical scale, and this is a very cheap $5 scale, but it's not the most accurate, it's got some error in it. So I'm going to elect to use my more precise electronic scale. I have that scale attached to the beam, and I can move this position of the scale anywhere along the beam. And then I have weights, my little test weights, that I can place on the beam at various locations to see what happens. And what we'll do is we'll measure and make some calculations on the moment arms and the results and determine what kind of forces we'll see on my scale as we do the experiments. Okay, before we conduct our experiments, let's verify a couple things. First of all, I want to make sure my test weights are pretty close to 1 Newton. So I've got my scale set up here. Let me zero it out. Now I can weigh my cups of pennies to make sure they're pretty close to 1 Newton. And okay, I'm sitting about 1.0708 newtons. So for these experiments, that's going to be close enough. Let me check the second weight. And that one's running about 1.06 newtons. Again, close enough for these particular experiments. So I'm going to go with that. Now, what I want to do is make sure my beam is going to be horizontal when I do my experiments. So I've got my strings and my spring scale set up so I get a relatively horizontal beam. I can check that with a small bubble level to make sure I'm pretty close. Again, it doesn't have to be precise, but you don't want a lot of slope to the beam because then you'll be working with components of the downward forces, and that's not good for this experiment. So again, close enough in the horizontal position for my beam. And finally, my calculations assume a massless beam. Now I could have calculated the center of gravity for the beam and built that into the moment calculations, but I'm going to assume a massless beam. So I can simulate that for my experiments by zeroing out the weight of the beam. And again, we'll make things close enough for this particular experiment. So once again, I will zero out my force with the beam attached to the scale. And now I'm ready to do these experiments. Now I'm just going to be looking at the force of the spring scale and the force of the downward test weights. So we'll see how things work out. Okay, so let's go on to our experiments and see what happens. Now here's a simplified force diagram of the system. We've got the pivot point here, represented by the red dot. We'll have the upward force being provided by the scale, and the downward force being provided by the test weight. Now, since the system is static, in other words, not moving, the counterclockwise moment must be equal to the clockwise moment. So now let's stick some numbers in here and make some calculations to see what the result will be. First of all, the clockwise moment, which is denoted by the black arrow and the 1 Newton downward force, 0.6 meters from the pivot point, is given here. Clockwise moment is equal to 1 Newton times 0.6 meters. Now the counterclockwise moment is generated by the scale. So we have the scale mounted 0.3 meters from the pivot point, and we don't know what that force will be. We want to calculate what that will be from this calculation. Now, because it's static, the clockwise moment must equal the counterclockwise moment. So we put in the values. 1 Newton times 0.6 meters is equal to F times 0.3 meters. And so we get 0.6 Newton meters being the clockwise moment and F times 0.3 meters being the counterclockwise moment. Apply a little bit of algebra, so we get 0.6 Newton meters divided by 0.3 meters is equal to the upward force provided by the scale. If we run through that math, we see that the upward force provided by the scale is 2.0 newtons. So let's go to the test setup and see if this bears out in the experiment. Okay, so let's see if our first experiment checks out and we get the proper result. Now what I have is my electronic scale set at 30 centimeters, 0.3 meters from the pivot point. I have my calibrated weight here, and I'll hang that at twice the distance, or 60 centimeters, or 0.6 meters. And theoretically, we calculated that the scale should be reading about 2 newtons. And if we take a look here, we see we're at about 1.97 or so, 1.99. So essentially 2 newtons. Now again, there's a little bit of friction in the system. Everything's not perfectly level, and things are not exactly precise. So it's not going to read exactly 2.0. Rarely will your experiments show you exactly the exact theoretical results, but we're very close. So it bears out that the theory is correct. Now let's move on to our second experiment. Now let's look at a slightly more complicated system. Now here's what we analyzed previously. We had our upward scale force and our downward 1 Newton force creating a clockwise moment. Let's add a second downward force of 1 Newton to keep things simple, but apply that force at 0.45 meters from the pivot point. So now we have 2 clockwise moments being generated and being opposed by the single counterclockwise moment. So now, since we summed the moments in this experiment and in this mathematical application, we'll see that 0.1 newtons times 0.6 meters, so that's the moment created by this force, is added to the moment created by this force, 1 Newton times 0.45 meters. And again, that's going to be equal to the force created by the scale in the counterclockwise direction. Now, if we do some multiplication here, we get 0.6 Newton meters plus 0.45 Newton meters is equal to F times the 0.3 meters, the distance our scale is from the pivot point. I can add those together, so it's 1.05 Newton meters is equal to F times 0.3 meters. Once again, apply a little bit of algebra. We get 1.05 Newton meters divided by 0.3 meters is equal to the force generated by the scale to keep the system static. If we run through that math, we'll see that the force F in the upward direction is 3.5 newtons. So let's go to the test setup and see if this bears out. Okay, so let's check the theory out on our second experiment. Now I've got my electronic scale still at 0.3 meters from the pivot point. Now I have 2 weights, both 1 Newton. I'll hang the first one at 0.45 meters. And I'll hang the second one back again at 0.6 meters. And our theoretical calculation said we should see about 3.5 newtons on the scale. And you see we're bouncing around a little bit because my weights are swinging a little, but we're at about 3.54, 3.6. So again, not exactly correct because of some of the uncertainties and irregularities in the system, but again, very close to what the theory says. So again, this bears out the theory of how to sum the moments and calculate results. So very good. Let's move on to the third experiment. Here's a setup for our third experiment. Now, rather than have the force applied outside of the spring scale, I want to move that force inward and place it between the pivot point and the scale. And I'm going to place that halfway between, so it's 0.15 meters. Now, if we look at the math, you see that my clockwise moment is 1 Newton times 0.15 meters. And that's opposed by the upward force being applied by the scale. So that's F times 0.3 meters. Of course, the distance between the scale and the pivot point. Do a little bit of the math. We get 0.15 Newton meters is equal to F times 0.3 meters. Once again, apply the algebra. 0.15 Newton meters divided by 0.3 meters is equal to F, the upward force generated by the scale. And if we do that math, we'll see that that F becomes 0.5 newtons. I should note, if we had the downward forces applied out here, the upward force needed to be applied by the scale was greater than the sum of those downward forces. However, if we move the downward force between the pivot point and the scale, we see that the upward force that's needed is less than the downward force. So let's go to the experiment and see if this bears out. All right, so here's the results from the third experiment. Now what I have is my 1 Newton test weight at 15 centimeters from the pivot point, or 0.15 meters, and the scale still at 0.3 meters. And theoretically, we calculated a 0.5 Newton force on the scale, and sure enough, we're bouncing around 0.5. So again, very good results from these theoretical calculations relative to the experiments. Now, something you have to keep in mind is I have this wooden beam, and this wooden beam has mass. Now, my calculations were based on a massless beam. So what I've done is I've calibrated or zeroed out my scale with no weights on there, with just the beam. And I can get that zeroed out so that it kind of simulates the fact that that's a zero mass beam. So I can actually calculate the center of gravity of that beam and calculate that into the moments and work that out. But I elected this time to zero out the beam and pretend it's a massless beam. Anyway, looks like the theory of the moments, summing the moments to get things in a static situation, are working out. So that's very encouraging. Always good to see theory match experimentation. Well, that sums it up for moments and how we use summing of moments to calculate the forces involved with a static situation. So hopefully you have a better appreciation on how you calculate moments, and I hope to see you next time on LabRat Scientific.